Hello, everybody. Welcome back to the Match Grade Podcast. I'm Butch. I'm here with the resident nerd Ed, aka Busta. And with us today is a very close friend of my father's and in turn a lifelong friend of mine, Jeff Siewert, a ballistics expert, I will say.
Thanks for having me. Appreciate it.
So we've never had a ballistics expert, on the podcast before. So Jeff, can you tell us a little bit about your background and, why this video is going to be so popular?
So back in 1979, I started with General Electric in Burlington, Vermont. They make Gatling guns for fighter aircraft. And I started there in the ballistics group back then and worked in that group for about 10 years and left there in 89 to go work for a company that I retired from, Aerotech Associates, and worked for 40 years in various calibers of ammunition, everything from 17 caliber up to 8-inch howitzer, and almost everything in between.
At what point do we stop calling it a howitzer shell, a caliber, and it's just a,
Well, I mean, if you want a break point between small caliber and medium caliber, the real break point is the body of the projectile engraved to spin the bullet. And so 50 caliber is a small arm. 20 millimeter, because it has a discrete rotating band, is considered a cannon caliber.
Okay.
So now you know.
That's pretty cool.
Did you just still refer to howitzers as medium caliber?
No, I don't.
Okay, good.
No.
For Butch, it might be a medium caliber. For the rest of us, Well, we're glad to have you here and glad to, have you share your knowledge with us. So where should we begin?
I appreciate the opportunity. We start with the basics.
Okay.
Okay. On the slide that will get put up here, we've got various rifle calibers, starting from 17 HMR, working our way up through 12 gauge, including 338 Lapua, 300 Win Mag. And what we have there is, as a function of rifle weight going across the top, start at 5 pounds and working our way up to 11 pounds, a sense of what the recoil energy would be. And the government did a bunch of testing to determine what levels of recoil people will tolerate. And there are some levels of recoil that nobody should tolerate because bones get broken.
Does that include the Butch side?
That includes Butch. That includes Butch.
Okay.
So in the color-coded rows and columns there, things in the light blue / light green is unlimited, less than 15 foot-pounds.
Okay.
You can fire that as much as you would like. Okay?
Beginner shooters.
Sorry?
Beginner shooters.
Absolutely.
Yeah.
Absolutely. In the blue is a limit of 200 pounds a day, and that starts at 15 foot-pounds of recoil energy and goes up to 30 foot-pounds. Now, what's in here on this graph assumes there's no muzzle brake, no flash hider, no suppressor. So
Any type of muzzle device that would throw off
to help dampen the recoil.
Got it.
Okay. In the pink is 100 a day limit for recoil energy between 30 and 45 foot-pounds. In the yellow is 25 a day, recoil energy between 45 and 60 foot-pounds, and then none is the red, over 60 foot-pounds. So that's your 300 Win Mag with a 5-pound rifle. Do not do that.
Is there a 5-pound rifle that will shoot a 300 Win Mag?
I certainly hope not. I certainly hope not. 338 Lapua until you get up to about a 9-pound rifle. Don't do that.
Now, you have this in this great color-coded chart. For our kind of regular listeners, what would 15 foot-pounds of energy, feel like? Is that like someone fist bumping you? Is that somebody, slugging you in the shoulder?
15 foot-pounds is actually fairly benign.
Okay.
It's noticeable, but it's not objectionable, in my opinion.
Okay.
I have shot 300 Win Mag with probably a 9-pound rifle. That's 34 foot-pounds. That's, let's just say, noticeable for most.
So if I punch Butch, he might feel
Punch you back. No.
30 foot-pounds of energy, that's about
Yeah.
that neighborhood.
35 would start a bar fight, I think.
Okay. So once we're in the 45 to 60, that's you're gonna feel that.
Yes, absolutely. And kind of the takeaway here is that heavier guns have less recoil.
Is there a definitive measurable spot where you get a gun that's so light with such a high caliber, like a 300 Win Mag in a 5-pound rifle, where forget about the effect on the shooter, just the rifle is just not going to perform at all?
In general, I have seen from various sources that the heavier the rifle, the more accurately it'll shoot.
Sure.
So the smaller the groups that will shoot. I need to make that technical correction. I would tell you that heavier is better when it comes time to pull the trigger. And then you have to decide, what am I willing to take out of the case and put on the bench, or take out of the case and take it to the field.
Yeah.
And a lot of that translates across the board for firearms in general. We know shooting a 22 long rifle, out of, a 6-inch handgun, that you're not going to feel anything like that. But if you shoot a 45 ACP out of your pocket 1911, there's going to be quite a bit of recoil.
Yeah, and you can get into problems with cycling from limp wristing, all of that good
Exactly.
stuff.
One of our fellow instructors, Tom, shout out to Tom, is kind of infamous for saying the nice part about a small pistol is it's small, and that's the end of the list. So we see often where people want to carry the smallest gun because it's comfortable and it's something they'll do, but then we have to try to convince them you're trying to find the trade-off between that and actually being able to be competent shooting it, which translates right to this, just with rifles and bigger ballistics and medium ballistics, as you were saying.
So speaking of bullets and cartridges and case material and things like that, there are different ones that are going to have different effects on firearms, right?
That's absolutely correct. There are lots of options these days for cartridge cases. The image that will get put in here shows you a brass cartridge case, steel one, aluminum, a combination brass and plastic, steel and plastic, and aluminum and steel. The shell shock cases are kind of new, interesting, very interesting development in my book. They have a steel body and an aluminum base, and you really need a metal on the base of the bullet. Plastics aren't yet strong enough to do that job by themselves. So that's why the two plastic offerings have metal in the base of the bullets. Okay, and they all work kind of remarkably well. Is the effect on the gun the same? No, not at all.
I was going to say, so all the materials for the case will essentially fire a bullet and make it leave the gun. It's just a matter of what it's going to do to the barrel and the gun itself afterwards. That's going to be different and dependent.
Yeah, so there's the function part, which most of them have that worked out, which is great. The other factor that we don't get a chance to really evaluate unless you've got a gun that's fully instrumented is a thing called the bolt load. Okay, how much thrust is coming back on either the slide or the bolt face of the gun? Okay, so for a blowback 22, we don't care about it because there's no lock. Okay, it's only for guns with a lock breech that we care about the bolt load. Okay, we'll talk about other mechanisms of building. in a little bit here. But the next slide that we have up here shows a comparison of the boat load as a function of the friction. There's a wet case, a lubricated case, there's a dry case, and then there's a dirty case. And the plastic cartridge cases, they're unable to shed any load to the chamber at the case chamber interface. They can't grip the chamber during the firing event. So those things have a lot of load going into the bolt.
Back into the bolt because they can't hold on to the chamber.
The contact stress is high, but you can't transfer any loading shear across the interface because it's plastic.
Mm-hmm.
It's plastic low strength material.
So is that why people would want a plastic case for low friction, or is that just something for a very particular crowd?
Well, it's I think for a very particular crowd. If you're on a special ops mission and you need to carry a lot of ammo for a given amount of weight, that's the choice you would make.
Got it.
It's not something, unless the gun is specifically designed to handle increased bolt loads, you wouldn't pick that, because your gun is going to fatigue and fail in much fewer rounds if you have a plastic cartridge case.
What kind of effect does it have with a situation like that where you don't have the lock bolt? Something
If the bolt's not locked, it doesn't matter.
doesn't matter.
Doesn't matter. I did some work, 3 years ago for a well-known gun maker on 5.7 by 28. And that's not a lock breech gun. That's a blowback operated gun. And interestingly, to me anyway, if you wanted to increase the net bolt load to improve the function reliability, you actually have to reduce the peak chamber pressure, which seems a little counterintuitive. But you've got less area on the base of the cartridge case than you do on the OD of the body. So if you want to increase the bolt load going back, you have to decrease the peak chamber pressure. Like I said, it's very counterintuitive, but that's what has to happen. It's a matter of how much strength, how much load relief do you get from the brass case as it interfaces with the chamber. So the other graph that's on here shows the fatigue life versus the increase in bolt load, okay? And you start off at kind of dry brass case being the baseline, okay? And as you change the interface conditions, the bolt load, generally speaking, with the exception of let's coat the case in sand, so you really increase the friction. Anything you do to the case usually drives the friction down. So lubricant on the outside of the case, water on the outside of the case, all of those things tend to drive the bolt load up because it reduces the friction between the case and the chamber. Okay, and those things reduce the fatigue life of the lock mechanism.
Got it. So if you think more friction on the case and the chamber, less bolt load on the rear.
That's correct.
And less friction, more lubrication, on the sides of the case, is going to result in more bolt load and a more fatigued.
Right. So
Okay.
it's kind of it's
I'm getting it.
it's the no free lunch thing. If you increase the friction between the case and the chamber, that's good for the gun, but it's bad for the cartridge case. Cartridge cases, we don't use a normal factor of safety in terms of their engineering assessment. We use a thing called percent of ultimate strain. How much can you stretch it before it fails? And what percent of that stretch does the case undergo during normal firing events?
So when you're wearing out the locking mechanism or putting more stress on the gun, are we essentially wearing out the action, the barrel, the bolt?
Okay, so what wears, like let's think of an AR-15 platform, because that one's simple and it's easy to Most folks can visualize that. What we're wearing out is the lock lugs on the bolt head and the lock lugs on the lock extension from the barrel. So those little fingers that stick down at the lock and turns into engages will wear because you've got an increased amount of load pushing on those fingers.
Got it.
So instead of, let's pick a number, with normal cartridge cases, let's just say that those things are good for 20,000 rounds. Okay, if you shoot polymer cartridge cases, or if you shoot lubricated cartridge cases, your parts life might be 5,000 or less. So it's a big deal.
That's chopping the life down by 75%.
A lot. That's the other part of the reloading thing that we'll talk about. When you resize the cartridge cases, you need to make sure that you clean that lubricant off as definitively and as cleanly as you can make them, because you'd rather lose the case than lose the gun. So let's talk bullets.
Let's talk bullets. Absolutely.
Okay. So again, in the graphics, you'll see there's a copper core bullet, and basically that's a drawn copper alloy jacket, and you take a slug of lead and you push it inside, and then you do some forming operations. And at the end, you've got a bullet. Okay. The next in line is a plated bullet. And we're going to come back to the plated bullet. But basically, what happens is you get a formed piece of lead that you put into a plating bath, and then through electrochemical means, they put on a coating of a few thousandths of an inch of, typically it's copper alloy. I'm going to dig into that because I can't hardly leave it alone. Okay, the next one is bonded bullet. And basically with that, you have a formed jacket and a slug of lead that's precisely dimensioned so that we keep the weight consistent. But then through either chemical means or thermal means, we bond the lead to the jacket. And you can't do the bonding process with an alloyed lead, so it has to be pure lead. Okay. Next is a partition. So we've got a physical separation between the forward chunk of lead in the bullet and the aft chunk of lead in the bullet. Once upon a time, Barnes made a alternate aft core material, which had a much higher density than lead, and it's MRX bullet, if I recall. And they're no longer making that, but that was a kind of an intriguing approach to solving that engineering problem. And then lastly is the monolithic bullets. And I've shot monolithic bullets since 2007 on all game that I eat. So
I was going to say,
nobody, to the best of my knowledge, nobody's ever experienced lead poisoning from shooting cup and core bullets at game and then ingesting the meat. But I'm like, if I'm going to feed it to my grandkids, I don't want to take that chance.
Somebody that usually eats some of the dinners you cook, thanks.
So, Jeff, is there a good example for each one? I mean, you talked about the monolithic a little bit, but what would be an example of why someone or some department might use a bonded bullet or the partition bullet, which I've never even heard of,
So the partition is John Nosler came up with that back in, I think it was the 50s. So that's been around a very long time. They're not easy to make well, because you have two cavities that you have to push into the jacket, and they have to be concentric and straight. So they can't be tilted. That bullet is designed to shed the front core and leave the back core in place as it strikes an animal, and so you get a good balance between expansion and penetration.
Hence the reason they had the one with the heavier weight in the back of the bullet. So
Generally
it's hitting
speaking,
harder.
yeah, generally speaking, that's correct. Randy Barnes, Randy Barnes, is it Barnes? I'll have to look that up. I don't-
Barnes bullets. Yeah.
Yeah, Randy Brooks, sorry.
Okay.
That's why I got confused.
Okay.
Randy Brooks at Barnes Bullets, he bought the company, kept the name from the previous owner. He came up with the modeled copper bullet, and that really revolutionized the non-toxic bullet business.
Hmm.
And so I've dealt with those for a long time. They're a very, very good bullet. They tend to be a little bit more difficult to get to shoot small groups compared to a copper core bullet, but in some instances they shoot better, and it depends a lot on a lot of details that we're not going to go into.
Yeah.
Well, let's talk a little bit about the plated.
Yeah, absolutely.
So the plated bullet, you can think of that as a bag of toothpaste surrounded by tinfoil.
Okay.
Okay, so it's not particularly.
Talking kind of terms I can understand.
So they're not particularly strong, and the plating, because of the thickness, and when you plate copper onto a bullet, they typically have large grain structures, which means they're very soft. So you're really counting on the skin, if you will, to hold the bullet together. So if you have a barrel that's, say, oversized, you wouldn't know unless you measured it.
Mm-hmm.
You may have some trouble with a plated bullet in your gun in terms. Okay, how about rifle bullets and ballistic coefficients? Okay, most people know, oh yeah, I want a high BC bullet. What do they mean? Basically, it's the weight divided by the drag and the area product. Okay, so the higher the weight, the higher the BC. The lower the drag and the smaller the area for a given weight bullet, the higher the BC you're going to get. And BC is just a convenient shorthand. I actually didn't deal with it in my professional career until just before I retired. It was kind of one of those things that we didn't discuss much because we were dealing at a much finer fidelity level when it came to looking at bullets. So here we're going to show you on the graphics 170 grain flat point, G1 BC of 0.189, 178 grain ELDX, BC of 0.552, and a 220 grain ELDX with a G1 BC of 0.65. So what does all that mean?
Yes, please explain.
I'll show you in just a little bit, but basically the length of the bullet is one of the things that is a primary determinant in terms of what twist do I need to stabilize the bullet.
Mm-hmm.
Okay, longer bullets need faster twists, not a surprise. They also, we'll talk about it in terms of terminal effects in a little bit, but the faster the twist, the more stability we're going to get on the bullet.
And that's where your 1 in 25, 1 in 12, 1 in 10. So 1 in 10 is going to be the most twist you're getting because it takes 10 inches in order to get a single revolution, whereas a 1 in 25 will take 25 inches. Is that?
That's correct. And in the ballistics world, we tend to use calibers per rev. And the reason for that is it makes it easier to compare the relative twist rates across different calibers. So a 1 in 8 twist in a 6.5 versus a 1 in 8 twist in a 30 cal, they're different critters.
Yeah.
So that's why we typically refer to the twist in terms of calibers per rev. Okay. All right. So what are the advantages of high BC? Better velocity retention, and you also get reduce crosswind sensitivity. So that's really the reasons we want to shoot high BC bullets. Okay, and the next slide, I have some comparisons: velocity versus range, drop versus range, and crosswind drift versus range. And all of these, for better or for worse, have the same velocity, even though that's not practical. But this just shows you why the flat point bullet would not be your first choice for a long range shot.
Yeah.
Velocity, the velocity degradation is much, much higher than the other two bullets. Drop is also much, much increased, drop versus range. So you're going to have to elevate the gun above the target to hit it. And then lastly, the crosswind, the drift due to crosswind is much higher with the high driven bullet.
Because it's getting affected that much more.
It takes the bullet longer to get there, so the drift is larger.
Gotcha.
Okay.
So BC is, like in a layman's terms, how efficiently a bullet moves through a medium without being affected by external factors or how much of an adjustment you might have to kind of make.
It is affected by the medium.
Okay.
And it's really if you're talking BC, the higher the BC, the better. And there's always some sort of reference with regard to the BC, or there should always be a reference, whether it's G1 or G7. And you need to specify that G number.
What does the G number indicate?
You really want to know?
I want to know, just because I'm curious.
G stands for Gavre, Gavre. It's the name of a firing range on the west coast of France, right on the Atlantic Ocean. I've actually been there.
That's awesome.
Okay. And basically they came up with a bunch of different standard bullet shapes. Those are referenced in the book. And the G1 shape is unlike almost any bullet that I've seen, either personally or professionally. G7's a lot closer. You really ought to think some about selecting the right G function when it comes time to use a ballistic solver to figure out how much I should hold over when I'm going to engage a target at long range.
That's cool. I like the backstory of the.
Yeah.
That is pretty cool.
That's why we have people like that.
Okay, shotgun slugs.
Now we're talking.
All right. So I guess you guys have a little bit of experience with shotgun slugs.
A little bit, yeah.
All right. So tell me what your experiences are.
We don't do too much with the shotgun slugs. There's a couple of drills we'll do, slug selects, changeovers, that kind of stuff,
Okay.
just to kind of push out some distance. But even there, the distance we're talking, we're
How far are you talking?
less than 100.
Okay.
Yeah.
I like to use the.
Outside of like a hunting kind of thing, but just like in the home defense kind of thing.
Yeah.
Yeah.
I like to use the shotgun slugs to zero
Yep.
my shotgun because it's much easier to see rather than a spread pattern of your standard bird shot or
Yeah,
buckshot.
where's the center of the stroke?
Right,
And
exactly.
How
You
much
can't.
does it jump around shot to shot to shot? So the Foster slug is kind of the go-to, and basically this is a cylinder with a half a hemisphere on the front end, and the base of it's hollow. And so what happens, as you can see in the slide, is that at launch, before the slug even clears the mouth of the cartridge case, as it's being fired, that thing collapses on itself and becomes a solid disc. It's like a dinner plate moving sideways through the air. Okay, and they shoot remarkably well in terms of small groups for a very strange reason. Basically, as you tilt it, it can't generate much lift to generate any swerve. So for short, they're not stable.
Yeah.
They're not gyroscopically stable. They're not statically stable. They're not stable. It's a bit of a mystery how they work as well as they do. But basically, those things just collapse, and that makes the slug fit very tightly to the shotgun bore.
Mm-hmm.
And it's really the angle of the bullet in the gun relative to the bore center line multiplied by the spin rate is a disturbance that causes the bullet to swerve off center line. If there's no offset because you smash the thing flat and there's no spin rate, you don't have much disturbance to send the thing into next week. So once upon a time, I gave a class over in Sweden to a guy who was attached to the military, who was part of the class, and he said he had seen guys done autopsies on guys who had been shot with slugs. He said it wasn't pretty.
Yeah.
So, yeah, use that at your own risk.
Yeah. Take that for what you will.
Yeah. So the other options, of course, is if you have a shotgun with a replaceable barrel, most of them are replaceable. Mm-hmm. You can buy a barrel with rifling in it and use what are called sabot slugs. And they have a little sub-caliber projectile. The sleeve on the outside is what we would call the sabot. And it grabs the rifling and imparts spin to the sub-projectile. And at muzzle exit, that thing splays out. Air resistance grabs it and separates it, and you can shoot those out to about 150 yards.
I've seen you do it.
I have done it. Thank you very much.
We got done hunting. Keith called on the radio and said, well, what do you guys want to do next? Boom! Jeff gets on the radio and says, I decided I'm going to shoot this deer. And that was when you first started carrying sabots. It was a long time ago.
Yeah. Yep. I wish I had been on the mic earlier, but there was a deer that had to be killed.
So the Foster slug can be shot out of a smoothbore or a rifle, or
You can shoot them out of a rifle barrel. It's not recommended, but yeah, it's possible to shoot them out of a rifle barrel. In fact, that's a test that could be done.
Are you getting any kind of performance added to it by going through the rifle barrel?
Possibly. One of the things that causes the slugs to swerve off of their flight path is a thing known as an aerodynamic trim. So the bullet, if it flies with zero spin and there's some asymmetry to it, that generates lift, and that causes it to go in one direction or another, and it won't come back.
And when we're talking these, we're talking general lead, so there's a lot of imperfections to give the little deviation to it.
Right. So if you fire it in a rifled barrel, that trim is basically, you could think of it as rolled out or nullified as it rolls. I mean, it's going to swerve around, but it'll land closer to your aim point than if you hadn't rolled it at extended ranges.
and on the other side, a sabot slug has to be shot out of a rifle to give it that spin.
Absolutely true.
If
And you would not be happy spending $5 a shot and not have it work like you wanted it to.
So not to be shot out of a smooth bore.
That is correct.
Got it.
Don't do that. Don't even try that at home.
Because of cost or because of damaging something? You're not gonna.
It won't stabilize.
It won't be worth anything.
It won't.
But it's not going to hurt the gun. It's
No,
just
won't-
useless.
Yeah, they won't hurt the gun, but it won't perform like you'd like it to.
You're just throwing $5
Just throwing
down
$5
range.
down the
You're
road.
wasting money. Okay, so here's the gyro stability question.
I gotta say, when you put this slide on, I got so excited
Why?
about that because I love the math behind it, and I love all the inputs and the fact that you can get a result by plugging in all your little variables, and
As long as you know what to plug in.
right.
Okay. Yeah, so kind of, I won't go into too much as to what's here, But the spin squared is in here at the numerator. The polar moment of inertia squared is also in the numerator. So the inertias are basically, you can think of them as the resistance to acceleration. So the polar moment of inertia, that's around the longitudinal axis. How much torque does it take to spin the thing up? That's part of it, okay? In the denominator, air density or medium density, depending on what we're talking about.
Mm-hmm.
The transverse moment of inertia, so if the bullet's flying this way, it's the resistance to acceleration in a direction other than the spin axis. Okay, and so the longer the bullet is, the higher the transverse moment of inertia. So you think about a barbell with weights on it. And if you take those weights and you smash them right to the center, you can jack that thing around very easily. You put those weights at the end of the barbell. Now it takes a lot of gumption to move that, to oscillate that thing. So that's a demonstration of the transverse moment of inertia. If you want the bullet to shoot good dispersion, you want to drive that transverse moment of inertia down. Okay, but for stability purposes, you don't want a big number. Okay, aerodynamic term in there, pitching moment coefficient derivative. So that's a thing where as the bullet tilts relative to its velocity vector, the forces that act on the bullet tend to try to dump it over, make it tumble. And if you spin it fast enough, you can avoid that. You can prevent that from happening. Okay. That particular thing, you have to use the software that I used my whole adult life. Or you can go measure it. You can actually measure it with a series of paper targets, spaced perhaps somewhere between 6 inches and a foot apart. Need a whole series of them. Need to have some higher math to figure out what that number is. Okay, so also in there is velocity squared. So spin squared over velocity squared, if you push the bullet faster, that ratio stays the same for any given twist barrel. So, oh yeah, I'm going to make the bullet more stable by making the velocity higher. No, you don't. You can't. That is not how that works. The only thing you affect by pushing it faster is the change in the pitching moment coefficient. So, word of the wise, if you don't have enough spin, go get a different rifle or a different handgun. You don't have to worry about handguns so much.
So math-wise, you're dividing by a much larger number and having a much smaller result for your gyroscopic stability then.
That's correct. Now, the thing that helps you is that transverse moment of inertia. And the longer the bullet, the longer it's going to take to develop that yaw angle. Short, stubby little bullets got a very small transverse moment of inertia, so those things dump over very quickly. All right, the effect of the rifling twist and stability, okay? So in the graphic here, we have up at the top the land and groove diameters going from smallest to largest, or going from left to right. And then down the first column is the twist in inches per revolution. And we start at 12 inches, 10, 11, 10, 9, 8, 7. And the numbers in the table indicate the twist in calibers per revolution. And like I said earlier, it's really the calibers per revolution that the bullet designers worry about. So, the table's color-coded like the recoil table, and kind of the red ones are what we would consider to be slower twist barrels. And the yellow crowd and the yellow ones are faster twist, and then the green ones, the light green ones are faster yet, and the dark green one is about the fastest one I've ever seen. That's like 300 blackout territory.
Okay.
Okay, my least favorite cartridge.
You're not the only one.
Well, okay, good. All right, so the gyro stability goes up by the square of the spin rate. So a little bit can go a long way. And when we compare cartridge A to cartridge B to cartridge C, I always like to think about the twist rates in terms of calibers per rev, because that makes it easy to make those comparisons across different bore diameters.
So is it as simple as if somebody wanted to take the same, let's say 308 bullet, and they wanted it to have more stability, instead of putting it in a 1 in 10 twist barrel, they decide to put it in a 1 in 8 twist barrel?
That does the job. That does the job.
And is it going to be that noticeable? Like, are we changing it in terms of factors of tens or hundreds?
Well,
or
so that from 1 to 10 to 1 in 8 is a 20% reduction or increase in twist rate, right? And the stability goes up by the square.
yeah.
So that's a 40% increase in stability, gyro stability. There might be a similar increase in dispersion. Just put that up there.
So why doesn't
So it's all a trade-off game.
so why doesn't everybody just make,
Fast twist,
fast twist 1 in 8, 1 in 10?
because the dispersion goes up. So that wobble is important. Why is that important? The magnitude of the wobble and the pointing vector of the wobble affects where that bullet's going to land relative to where you aimed.
And that's a predictable variable?
If you know how big and how much, and what direction, the answer is yes.
Yeah.
Most of us don't have that luxury.
I was going to say, I'm still wrapping my head around the concept that bullets in general wobble, and it's not just...
Most people do. And most folks have in their head, if the bullet's wobbling, it's unstable. That's untrue. That is patently false. Okay? The wobble happens to virtually every bullet that you ever launch from any firearm. Okay? And the question then becomes, do you have enough twist to keep the bullet gyroscopically stable? Most bullets that we shoot do. The next question we ask is there enough spin and other parameters for the yaw, any yaw that's present at muzzle exit, to decrease as the bullet flies downrange?
Decrease meaning stabilize?
It gets smaller.
Okay.
So you might start out with a first max yaw. So the yaw is the angle between the velocity vector of the bullet and the bullet axis. Okay. So if that angle gets smaller, it's going to wobble like we've shown you. It's going to get smaller as the bullet runs downrange if the bullet's dynamically stable. And virtually all of the bullets that we fire, either in a rifle, all the bullets from a rifle are both gyroscopically stable and dynamically stable. Handguns are a little bit of a different thing. Anecdotal evidence that I've seen from a couple of gun makers would suggest that they might not be dynamically stable in some instances.
That's why I can't hit with the pistol at past 200 yards.
Use that as an excuse.
Okay.
I'm firing a dynamically unstable bullet, and that's why.
That'll be my tagline.
So the other picture here on this slide is a picture that I took that I fired at a range, and it was a hollow point bullet, and the hole cut by the hollow point is not concentric with the outside diameter of the bullet. That means that bullet is flying with a non-zero angle of attack at that particular distance. So it happens all the time. In fact, I'd go so far as to say there are very few bullets that we fire out of any firearms that we own that exit with zero initial angle of attack.
So does the wobble minimize once the bullet approaches target or when it hits, or is the wobble just a factor that's always going to be consistent with the bullet, along its flight path?
So I mentioned earlier that it's the magnitude of that wobble and the direction of the wobble that cause dispersion, cause the groups to be bigger than we would like. Okay, so we can't, unless we have a very sophisticated measurement system, we don't know where or how much from a wobble perspective. Generally speaking, rifle bullets would start with a wobble that would vary between a few tenths of a degree and say 1.5 or 2 degrees, but they'll decrease very rapidly. So by the time the bullet's gone 50 yards, 75 yards, the bullet is now flying with an angle of attack that's less than 1 degree.
Gotcha.
Okay. Handgun bullets, I think the jury is still out. Okay, so bottom line, there are things that you can do to the bullet from a design perspective and from an interface perspective that make it shoot smaller groups. Okay, less clearance between the OD of the bullet and the ID of the throat in the barrel tend to make the bullets shoot smaller groups.
Isn't that back to the slug? You mentioned that when it expanded,
That's
you're getting
yeah.
there, and that's why it was
That's one of the reasons they shoot.
bafflingly
Yep.
well done.
Yeah,
Okay.
even though the thing's not stable. The smaller the wobble and the more consistent the direction of the wobble, the smaller groups we're going to shoot.
Does that mean the smaller impact hole as well then, or?
So here we have 3 different target imprints. Okay, the first is perfectly circular, which is what we would normally expect to see from a rifle at reasonable ranges where the bullet's still supersonic. The next one is not quite circular. The bullet's got a little bit of angle of attack, okay? And this would be a normal impact at a subsonic velocity. So the bullet has entered a regime where it's gyroscopically stable, but not dynamically stable. And so the bullet flies with a persistent non-zero angle of attack. We would call it coning motion. And it flies with a persistent non-zero angle of attack that revolves around the velocity vector. And that angle of attack is typically between 3 and 5 degrees. Okay, not anything horrible.
No, is that because the bullet is now approaching such a distance that it's just slowing down as a result, or it's passing through a different media?
Do you really
or?
want the technical description? It's a change in the Magnus force center of pressure, which changes the Magnus moment.
Yeah, did you know that?
I was waiting for a really cool French story behind it, but
So now you know. So now you know. Yes, so it develops what's known as a Magnus instability. Okay, an increase in the Magnus moment, subsonically. And that only happens subsonically,
okay.
okay? And it only arises because the bullet is spinning.
So
It's probably more than you wanted to know.
No, that's actually everything I wanted to know. I have to know. I love to know.
Yeah, so now you know. And the last image I have on here is what we would call a keyhole. And at long range, if you get this imprint, What it really means is you hit something else on the way to the target. Okay. Now, you can see these keyholes close range if the twist isn't fast enough to provide gyro stability. So if you fired, I'm going to pick a number, an 80 grain 224 bullet out of a 1 in 12 twist, you get that impact. And it'll all be tightly clustered. The bullet's not gyroscopically stable. Okay, so long range, if you see those keyholes, it means you've probably hit the dirt or a rock or something. Target frame, a bird in flight, who knows?
I've seen that. Yeah.
Randy Johnson.
And then you get to go home and eat duck ass.
We'll tell you the duck is.
Yeah.
All right. Let's talk about barrels. Twist rate, that affects gyroscopic and dynamic stability, internal geometry, what shape is the land, the forcing cone angle has a play in the engraving force as the bullet travels into the rifling, number of lands and grooves. We can talk about production methods. There's a lot to learn about barrels, and we're going to dive in right now. Hammer forging. Do you guys have any firsthand experience with hammer forged barrels?
I know they're widely advertised, and everybody either talks about hammer forge or cold forge or something forged.
Same. Those are essentially used interchangeably. Yeah, basically, there's steel hammers that rotate around the barrel blank that hammer the snot out of the outside diameter and make this thing close around a mandrel on the inside that has the rifling form in it. And then as the material gets displaced, the mandrel moves the blank out.
So eventually you get a full length of barrel that's constantly being beat on along the mandrel that has the lands and the grooves, I'm guessing?
Yes, if the barrel has lands and grooves.
Right.
I have a Remington 870 shotgun, and the original barrel that I had, the smoothbore barrel, was, I'm sure, made by hammer forging process. And so mandrel has no rifling on it. So that's just the way they made it. It happened to be expedient to make it that way versus gun drilling it and then honing it. And so you still have to start with a very high precision blank when you use this process. So they have to carefully control the outside diameter of the blank, and then they go through and they hone the inside diameter of the blank as a consistent place to start when they do the hammering process.
So this kind of blows my mind a little bit, because I think for the longest time, I thought barrels were made by taking a blank cylinder and drilling the lands and grooves and the rifling into it, rather than putting it over a mandrel and beating it into that shape.
And so there are lots of different ways you can make a barrel. What you've described is one of them. The hammer forging is another. There's a few more, some of which are common and some of which are not so common.
When they're beating this for the hammer forge around the mandrel, how are they doing quality control over thickness of the barrel as it goes down low?
They're monitoring the load that is put into the hammers.
Okay, yeah.
They're monitoring, and then once they're done with it, they'll go through and check the dimensions.
So at a given spot, along the barrel, maybe this many hammers beats this many times before they move it another, couple millimeters or centimeters, and then they beat it some more for a period of time, and they move it some
And
more.
typically these things are tapered, and so they and we're at, let's pick a number, 5% of the 105% of the finished diameter, and then as you get closer and closer and closer to where the hammers are, it gets closer in dimension to what the expected dimensions or preferred dimensions are. Okay. So that's just one method of making the barrels. The other dimensions, the other methods that are common are shown here. Single point tooling, and most of the bullet makers, when they pick barrels to do their testing with, they're picking single point tooling.
No, why is that?
They feel they get a more consistent product, and they're more likely to be able to decide if a lot of bullets is good or not using a single point tool barrel.
You said they feel like, are they right?
That's on them.
Okay.
That's on them. So in single point tool, there's a thing called a broach stack, which this one shows what would be referred to as a gang broach, where the rifling is in a single tool, and the rifling twist is in there, and they basically just pull this through the barrel blank, and that cuts, half a thou off. But each cutting surface cuts off half a thou at a pass, and then they pull that thing through, and the rifling is totally done. So the broach stack for small cal barrels, they could do basically one tool to cut all of the rifling depth. For medium cal barrels, what they do is they put in a single wafer that cuts all of the grooves at the same time, and then they incrementally step up in diameter. So they're taking a half a thou at a pass, and the rifling depth might be 20 thousandths deep. So they have to make a stack of 20 broaches that all line up with the key on the mandrel that pulls them through the barrel.
And one pull cuts the whole thing.
And no, you make one pass, you swap that wafer out, you put a new wafer in.
That makes more sense to me.
Now there you go.
I was going to be impressed if they did it all in one go.
And usually medium cal barrels are gang twists, so they have to put relief angles on the cutter so that they can change the rifling angle as a function of travel.
That seems like a lot more work than your hammer forged mandrel beating method.
And there's very good reasons why they do that. And we'll cover that on another podcast. Okay. And the last one I have in here is the button rifle. Basically, what happens is they grind some grooves into a carbide button. I hate to use that word, but it's a piece of carbide tooling that they grind the lands into, as it turns out, and then they pull that through the barrel. And there are very high stresses generated, and it actually squeezes the steel into a land. Okay. And so that those quite high stresses are generated as a result of that particular forming process. And that's about all I'm going to say about that.
Okay. Probably.
Well, you can use lubricants. The guy that I visited that used that method to make barrels actually plated copper on the inside of the barrel as a lubricious metal, and then he pulled that through the barrel and then chemically etched the copper off of the internal surface, and then continued the manufacturing process from there. He did hand lapping, that sort of stuff with the barrel. So there was additional work that had to be done once he was done actually forming the rifling.
Holy cow! That seems like a lot of.
There's way more to it than you ever thought possible.
Yeah.
Okay. Barrel land geometries. There's what we would call square rifling. which most folks are familiar with,
Mhm.
and then what we'd call polygonal rifling, which is a very shallow, slope-sided driving surface to the barrel land. Okay, and the polygonal is easier to make with hammer forge and button rifling. You don't have to move material quite so far. You take that approach. And the question then becomes, is there an advantage? And the answer is, yes, there is. So this graph shows you the test that was done in a small cal rifle for the U.S. government. And it shows the relative dispersion for 3 different barrel twists. Over on the far right-hand side is a 1 in 12 twist. In the middle is a 1 in 10 twist. And on the far left-hand side is a 1 in 8 twist. And the baseline was a 1 in 12 twist, which is 40 calibers per rep. And if we believe that the angle of the bullet in the gun times the spin rate is one source of dispersion, and the CG offset radially from the bore center line, that offset multiplied by the spin rate is a throw of the bullet. So those are the 2 dispersion sources that are typically found with small cal bullets. If we believe those 2 factors are what drives the bus in terms of group size, then the expected dispersion should follow that black diagonal line going from the baseline at the far right in the middle and then trending upward as we go to the left. That's what should happen if those 2 things are what cause dispersion. Only. If those 2 things only cause dispersion. And what we see from the test was not that, which was, to me, intriguing. Like, it didn't behave like it was supposed to. Like, what's going on? I think I know. But, I mean, we have
Now
to.
you get to test.
Well, and that's why we did the test, So there are 2 different rifling types here, and we have in the red, it's the standard square landed groove geometry, and in the green we have the polygonal land geometry. And you can see at the 1 in 10 twist, there's a definite offset in a smaller group size with the polygonal. And to me, that's intriguing. Is the minimum land diameter with the polygonal smaller? Possibly. But I don't have a drawing of the barrel, so I couldn't check it. There's no way to check it. It's likely it was. Okay. So, and then the other thing that was interesting to me was the fact that the trend with increasing twist rate was much different with the polygonal rifling geometry than it is for the square landed groove geometry. So that was another intriguing thing. So if you have to pick the polygonal.
Pick the polygonal.
If you're going for a custom barrel, they are easier to keep clean, and I think that's part of the deal.
So, hypothetically, in an imaginary world, if you were to take a Foster slug and shoot it out of a polygonal rifled shotgun barrel, you would have it even more accurate than out of your standard. Theoretically,
We would. There's a lot of facets to that design space, but the answer is yes. But we would pick a different twist rate.
Right.
So just roll the trims out, you don't need much spin. Okay. So the spin that they've got for the current rifled shotguns is way more than you would need to shoot those slugs accurately, more accurately. Okay, much more, and that's kind of what you don't want. So, any experience with muzzle loaders shooting round ball?
Very few.
Only with you.
So with a round ball, you want as low a twist as you can get, simply because the bullet is not particularly aerodynamic, and you want it to roll to cancel those aerodynamic trims out, but you don't want to move it any faster than that because it tends to throw the ball. All right, the next image that Ed's going to put in for us is a cross section of a barrel it was a production barrel from a off-the-shelf firearm that somebody decided they were going to modify and put external flutes into the OD of the barrel. The idea being, I'm going to make it cool faster.
Yeah.
I'm going to make the barrel stiffer.
The idea being Joe Blow in his garage knows better than the max amount of engineers.
Yeah, and so I don't know the backstory behind the guy who modified the barrel. All I've seen is the results, and it turned out to not end too well.
Do you know if the ammo that he was shooting was his own little custom brand, or was that factory also? Or don't you know?
I do not know.
Okay.
I do not know. All I know is I went to visit the guy who makes the polygonal button rifle barrels. And he said, there's a guy up the street who has a barrel that you might want to look at.
Oh, so you actually took these pictures. These are yours.
You got it.
Of course they are.
Yes. I asked permission. I asked permission to take these pictures and use them. Yeah, sure, go ahead.
Mm.
So here we are. You're almost famous.
Other than we just won't mention your name.
Yeah, exactly.
I can't believe the bend in that barrel as a result.
Yeah, so if you look just in front of the cartridge case mouth, like 2 or 3 bore diameters, there's this little semicircular blip. And I think that's where the fracture started. And when you take material away from the OD of the barrel, you reduce its capacity to handle pressure.
Yeah.
Okay. And it's particularly critical where the bullet experiences peak pressure in travel. So they didn't know anything about where the peak pressure occurred. They thought the pressure was all back in the cartridge case. And in cutting the external flutes, they put it in a place that was particularly bad. And so this barrel split after somewhere in the neighborhood of 50 shots.
Do you know what kind of rifle it was on?
It was
Just
on a bolt action 300 Win Mag. And like I said, I don't know if it was factory ammo or.
That answers my question. I was just kind of curious what kind of rifle.
That kind of doesn't matter.
Yeah.
Doesn't matter. So the guy's hunt was ruined. He had to go pack his ass out to the hospital to get stitches. So yeah, external flutes. You need to have it done by someone who knows what the heck they're doing.
Mm-hmm.
So the next slide we have is what factors are important for long-range shooting. And I have a little target graphic up here, and we have a displaced shot group, and we show 2 categories of arrows. The first is a bias, a displacement horizontally and vertically of the shot group, and that happens as a result of winds, non-standard average muzzle velocity. Those are kind of the 2 important ones. Okay. And then the random errors are the result of things that the shooter can't control. Bullet to bullet to bullet, or shot to shot to shot.
Is this where you tell Glock shooters how to stop shooting low left?
Yeah. Just
Be better. That's how you do it.
just aim high right. That's good. Does that work?
I've seen it work.
Okay.
I'm looking at John Daly.
Okay. Yeah. So the random errors are the things that the bullet developers and bullet manufacturers work on. All they care about is what's the random part. How small can I make those groups in the factory? They don't give a flying rat's rump about how far does it hit off the mean point of impact, off the aim point. They don't know and they don't care. Okay. It's when you take that ammunition to the field that you now care about where does the center of the group hit relative to where I aimed.
Okay.
That's why you zero the gun.
Yeah.
The two categories are the bias, and again, you can have that displaced from winds, from a non-standard muzzle velocity. Those are kind of the two big ones. And then the random errors are quality of the bullet, the variability in winds will cause the impact point to scatter, variation in drag, variation in muzzle velocity. All of those things contribute to the magnitude, along with the range, contribute to the scatter of the bullets around the displaced mean point of impact.
When they start doing stuff like this, do they start in any kind of a proverbial vacuum to get a solid starting point and then take it out in the field and allow the other factors to come
When you
into
say
it?
in a vacuum, you mean in a test lab.
Yeah, but like how precise is that environment kept?
They don't.
They try to eliminate like all factors to get to a certain starting point and then take it out
Right. So the gun
to the real world.
Yeah, so the gun is held in some sort of fixture.
Right.
It's in a they have linear ball bearings, for instance, and it's on rails. So they do their absolute best to minimize any variation in the test procedure.
So then when they start experimenting around the variabilities of why it's going here or going there, they've eliminated as many variables as possible, and now we can just focus on what's causing this.
Right. So one of the customers that I worked for, they were doing development on a Sabot slug, and they found that changes in the thickness of the over powder wad affected the dispersion of the ammunition. You know, I was very impressed that they found that. I was very impressed they found that.
They probably were too. It probably took them a long time.
Well, and they worked long and hard for that. Certain.
So just because it's the namesake of the podcast, so match grade ammunition, is it due to higher quality of materials, quality control, in minimizing those kind of random errors as much as possible versus generic factory ammunition?
Absolutely. I mean, there is a manufacturing component. There's also a selection of material properties component. We're going to do this number of draws to get the jacket to this hardness so that the bullet is as least sensitive as we can make it in changes from barrel to barrel to barrel in order to make that product more robust. So there's a lot to it. Let's go on. Why reload ammunition?
It's cheaper.
Yep. Is it better?
Not nice, but
Depending on who's doing it?
Yes, it is. It can be if you pay attention.
sure.
Can be if you pay attention. Have I had some Fukas of my own? Yes. 300 Ultra Mag with no primer in it. Powder, but no primer. Oops. Now, I've also done the same thing with the same cartridge, primer, no powder. Like, oops, how did I do that? It happens. Pay attention. Pay attention. Yeah, and interestingly enough, the 300 Ultra Mag with a Magnum primer and no powder in the case doesn't generate enough pressure to move the bullet from the case mouth.
Really, not even that. Didn't get into the.
It didn't
even make it
move
into the.
a millisquidget. Okay, So yeah, but that's different from cartridge from cartridge to cartridge. There's no way to know prior to doing that test. If I had filled
That's
up,
funny that you call it a test. When a second ago you just called it a screw up.
it was a screw up test. It's kind of a,
If you got the right mindset, every screw up can be it could be a test.
it's flip sides of the same coin.
Yeah.
So if I had filled that cartridge case, let's just say with little ceramic bits that were of similar dimensions and geometry to the propellant that I normally load, and I pushed that bullet in there and fired it, would I have generated enough pressure to move the bullet from the case? The answer is likely I would have. Why would we reload? Custom loads. Smaller groups, less recoil. Finding a reliable source for obsolete or hard to find ammo. I have a buddy in Colorado who's using 7mm Remington short action ultra mag, and until a week ago he couldn't find that ammo in the store. It was nowhere to be found, and he did find it recently, over $80 a box.
Wow.
Ouch.
Yeah.
Right. So it makes a good hobby for folks who have too much time on their hands.
Not me.
You get the satisfaction of rolling your ball. It allows you to do more shooting for a given ammo budget. Better reliability if you pay attention. And less reliance on what's on the shelf at the store.
Yeah.
And some of those are actually quite valid reasons for taking up that hobby. Are you going to save money? I haven't yet. I've been at it for 40 years.
Yeah.
But I really enjoy loading my own and taking home venison
Yep.
that I have killed with the ammunition that I load. So typical firearm operating parameters. This is just a list of different firearms listed by caliber, what the bore diameter is, what the bullet weights are, the peak pressures. And, there's an air rifle in there, so that's, 3,000 PSI. That's kind of pushing it. That's it's not a Springer air rifle. That's one with a reservoir that you pump up. Velocity and then muzzle energy in foot-pounds. So it just goes through the various and sundry cartridges and lists all of the parameters that where these different firearms operate. And you can see that, gee whiz, the 12 gauge peak pressure, not even 12,000 PSI. That's kind of paltry compared to some of the rifle cartridges.
You're trying to accomplish a completely different goal, though.
You're trying to launch a big, heavy mass at some reasonable velocity.
Which Jeff normally calls pumpkin chuckers.
Indeed. Indeed. Okay. Different propellant types. So this slide shows you the different type of propellant geometries that are out there. You have a flake geometry, a sphere, cord, single perk, and a thing called C4. Not to be confused with the explosives.
I'm super excited there.
Not to be confused with the explosives.
When you start loading them with the C4, that's where we get into the major ones, right? Major bore. I mean, you had medium bore that we talked about at the beginning. I'm making jokes.
Actually,
Do not load your ammo with C4.
that one was used in a development test for sniper ammunition, and the group sizes that were shot with that propellant were kind of stunningly small. But the downside was we didn't really get to fiddle with the ignition system enough. And so the velocity variability was unacceptably high. So I'm kind of disappointed we didn't get a chance to further explore that. But so these are the different geometries that you might encounter. The cord propellant is kind of not widely used. About the only one that I can think of off the top of my head is Vita pistol powder, and only one flavor of that uses that particular geometry. So, but everything else is fairly common, and it just depends on what your goals are for the reloading process.
I see that the C4 is not readily available for reloaders yet, so I cannot go into my Sportsman's Warehouse or Bass Pro shop and ask for a jug of C4 yet.
No, you cannot.
I mean, you can.
Might raise some
But
eyebrows.
you're just not going to get any results out of it. Or at least you're going to
Hello, ATF, we got a Yeah, so the C4 was interesting in that it had 4 perforations in it. And basically the propellant geometry that you pick is one of the determining factors of what's the peak pressure. So for the shotgun, because the peak pressure is so low, it's tough to burn that powder out. And as a result, we have to go with the flake geometry typically.
Mhm.
Okay, so the stuff is very, very thin, and it's easy to burn up. With rifles that operate at 50 or 60,000 PSI, it's much easier to burn those out. So we can physically have larger propellant grains. A dimension called web. And do I have the web down? No, I don't have the, do I have the web? No, I don't have the depiction of the web on there, right? But the web is the smallest dimension of the propellant grain that you have to burn through to have the propellant grain completely consumed. Okay, so for the flake, it's the thickness of the flake. For the sphere, it's the diameter of the ball. Okay, for the cord, it's the outside diameter of the grain. For the single perf grain, it's the difference between the inside and outside diameter.
Mm-hmm.
That's the web. Okay, for the C4, there's a couple of webs. Okay, so
Of course there is.
that makes life considerably more complicated.
Is that why they couldn't get the velocities that were agreeable to them and they threw it away? Or
Well, it wasn't that it was the velocity variability that was the issue. It was, instead of having standard deviation of velocity of say 7 or 8 feet per second, theirs was at 12.
okay,
So from a sniper perspective, we'd prefer to get
they
smaller.
really want.
Yeah, and that was kind of a 50% bigger, and that's a problem.
Yeah.
So, okay. And then whether you're talking single base or double base propellant chemistry, single base is just nitroglycerin plus a few stabilizers and other things. Like the graphite on the outside of the propellant grains is there to help reduce your sensitivity to static discharge. So when you're pouring the stuff, from the container into your powder measure, static is generated. You don't want that to set off that powder.
No.
So that's why they coat them in graphite. Every grain that's out there is coated in graphite.
Don't learn anything else from this podcast. Just learn graphite's good.
Graphite's good. So the double base propellants have, in addition to nitrocellulose, they have nitroglycerin mixed in with them. And that percentage is, somewhere between 5% and maybe 15, maybe a little north of there. And that just adds energy to the mix, which helps you, for a given fixed peak pressure, boost the velocity.
So the different types of grains, do they burn hotter or faster or longer? Does that change at all, or is that the...
Here's a good answer for you. It depends. Okay. It depends because one of the things there's 2 factors that control the relative quickness of the propellant. The first is the thing we call the web. That's part one. The second is a chemical coating that's put on the outside of the propellant known as a deterrent. And that delays the combustion of the propellant. So if we want to maximize the velocity, we want to have as big a reservoir as possible of gas behind the projectile at peak pressure. The way we do that is to delay the burning of the propellant until the bullet hits that travel at peak pressure. You want to push the travel at peak pressure downbore as far as possible. That raises the average base pressure versus travel. And that maximizes the velocity. The other thing that does is it also, at the same time, pulls the travel at all of the propellant burn in closer to the chamber, which also helps to raise the velocity. So those two factors are why you put deterrent on the propellant. Okay, let's move on. Okay, different powder types. So, what I have here is a plot of surface area to volume ratio versus web size. So we mentioned that the web size was kind of a controlling factor in what application we picked. Low pressure, we need small webs. Higher pressure, we get away with bigger webs. And so here is kind of a graphic that shows you where the flake powders live, where the ball powders are, and then where the tubular powders are. And basically, what your application is really determines what powder you're going to use, what peak operating pressure, what's the expansion ratio, the ratio of the total barrel length, that volume plus the case volume divided by the case volume. That's the expansion ratio. It's kind of the inverse of the compression ratio for cars. The larger that expansion ratio, you pick a different solution based on what you're trying to gain.
Yeah.
Okay, and you need to burn out the powder before you get to muzzle exit if you can manage that. Some powders, some applications like pistols, it's pretty tough to do.
Yeah.
And what happens as a result? You ever fire at night?
Yep.
What happens?
Muzzle blast.
It flash.
Muzzle flash. Yes.
Yes.
Muzzle flash.
Yeah. Yeah, and that's not a good thing.
No, it's a waste too.
You're basically wasting energy when you have that condition.
I'm not one that likes to waste energy.
Well, and there you have it. So in addition to the flash part, particularly for precision rifle bullets, we want that powder to burn out prior to the bullet achieving muzzle exit so that the grains of powder can't hit the bullet. Bullets are most sensitive from a dispersion standpoint to loads applied at their base. What factors increase chamber pressure? This is not rocket surgery.
Yeah.
Okay. So first, increased charge of a given powder. Everybody's got that, I think, right? If you put more juice in the can, you're gonna jack the pressure up, right? If you use the identical charge rate of powder with an increased relative quickness, I think everybody can understand that one. We're good with that?
Yep.
Okay. Increased mass of the projectile.
Sure.
Yep. So what happens there is you push on the bullet and you've got a fixed amount of pressure behind the bullet, which means a fixed amount of acceleration. Okay. So if the bullet mass is up, that pressure doesn't give you the same acceleration, which gives you less displacement of the bullet, which means you have a smaller volume. You're going to vent that gas into a smaller volume, which is going to jack the pressure. Okay. Increased bullet engrave length, so that increases the resistance of the bullet to the inbore travel. Increased bullet stiffness, in other words, how easy can I compress the bullet by the rifle? All copper is really tough to engrave versus a cup and core bullet. So those things affect the piece pressure. Decrease free run to the start of engraving. Got that one?
No, I'm still on the other one.
Okay.
With the
same
with the barrel rifling. So now back to the square cuts or the polygonal.
Yep.
That can now affect what you end up having to do. So if you're making this ammo shooting and you got it all set up for rifle X that's got square cut, and then you just take the same ammo and you go shoot it through polygonal, you're getting
Could be out to lunch.
You're getting different
And that's
stuff.
the situation I'm in right now.
Okay.
Yeah, so I had a bunch of ammo loaded up for my 30-06. I was using a 168 grain monolithic bullet, and I took the firearm to the gunsmith, and I was like, I want a new barrel. Well, I got a new barrel put on it, and ended up getting a new receiver for me, etc. But long story short, I got a bunch of ammo that was okay with the previous barrel, and it's scary to think about shooting that in the new one with a polygonal rifle.
Yep.
With a faster twist.
Yeah.
Twist I'm not worried about. It's the polygonal rifling versus the square.
Yeah.
Okay. So decrease free run and start of engraving. Good with that? So if you pull in the start of engraving the bullet, when we start to engrave the bullet, that's when the engraving pressures go up. That drives the combustion pressure up.
Sure.
Okay. So if we pull that in, that's going to dramatically drive pressures up.
PV equals NRT by.
Yep. So the basically the V gets smaller, which drives the pressure up.
Yep.
Okay. Decreased internal case volume relative to baseline. So if you have Brad X cartridge cases, which have a certain amount of, let's just say, 10 cc's of case volume, and you then drop the same primer and bullet into brand Y cartridge cases, which have 9.5, you have less internal volume. Pressures are going to go up. End of discussion. Okay, and then lastly, decreased barrel internal dimensions. So if the lands are smaller in diameter, it's going to drive the engraving pressure up, and ditto with the groove diameter. Okay. Now, what happens if you just change the loaded cartridge length? Two things happen. The first of which is let's just say you're going to push the bullet more deeply into the case. Two things happen. First thing that happens is you decrease the internal volume in the case.
Increases pressure.
Which tends to drive the pressure up. The other thing that you do is you increase the free run to the rifle, which drives the pressure down.
But that doesn't necessarily mean that it's going to cancel out.
It doesn't mean it's going to cancel out. You have to, the best way to monitor that for the home experimenter is to monitor velocity. And the velocity doesn't ever come for free. If the velocity's up for a given powder charge, if the velocity's up, the pressure's up. So my 300 Ultra Mag, I played with the seating depth, and the closer the bullet got to the start of rifling, the higher the pressures went.
Okay.
And that's that. Any questions? By the way, if you have any questions, they can pester you guys.
Absolutely.
And you'll forward the questions to me, and I'll answer them. Or they can go right to my website, bulletology.com, and pose them there, happy to answer them. The book, Ammunition Demystified, is available at Amazon and Barnes & Noble. I just checked the other day about the reviews, 4.7 out of 5.0.
All right. Good for
Not too
you.
bad, not too shabby.
Yeah.
I was gonna say I just blew through Butch's copy of it, in a couple days. So it's a great read. Plus, it's not too dry because you intermix your war stories in there with it, which adds a nice practical background.
As I was writing that, I was like, you know what? This reminds me of something that happened. And I was like, well, let's put them in there.
Mhm.
And so that's what I did. And hopefully you come away with the idea that even if you're an expert, you could still screw things up.
Yeah.
Awesome. Well,
That's what I got, guys.
Jeff, thanks so much for coming onto the podcast. We appreciate it. And
Thanks very much for having me.
yeah, we'll probably see you again
I hope so.